This video is going to be an introduction to antiderivatives. So just as before, when we had a quantity and we wanted to find the rate of change of that quantity, we had to differentiate the function, right? So now, and so we were able to apply rules of derivatives. Now, the idea is whatever we want to do in mathematics, we also want to be able to undo or go backwards. And so we want to maybe perhaps start with the rate of change of a quantity and get back to the original quantity itself. And that the verb form of that action is called antidifferentiate, or antidifferentiation is a noun. And the tools that we are going to be using are antiderivatives and integrals. Okay, so these are going to undo derivatives. Okay, so the question that we need to answer is, if we're given a function, f of x, okay, so we have perhaps a polynomial or logarithm or trigonometric function, what is the antiderivative of that function? So when I encounter a function that I want to antidifferentiate, I need to think to myself, what did I have to differentiate to get this function? So if I view this as the derivative, then what did I have to differentiate to get to this? Well, this is a polynomial, right? So if I differentiated a polynomial, I had to use, okay, so I'm thinking I had to use the power rule. Okay, and what that said was, well, I had to bring the constant, or the exponent down in front as a coefficient of x and decrease the exponent by 1. So I think if I were to look at the antiderivative, it would just be x to the fourth in this scenario. Okay, and so in terms of notation, the antiderivative is denoted with typically an uppercase letter corresponding to whatever the function name was. So if we had a function g of t, say, is equal to something, then the antiderivative, we would just use the capital letter for that. Okay, and so what we can do is, if we're ever doubting that our function was incorrect, we can check it. Okay, and the check is just to differentiate what we had, or what we found. So if I take, okay, so f of x we said was x to the fourth, then to check that this is indeed the antiderivative, I want to compute f prime of x, which would be x to the fourth and the derivative of this. Okay, if I differentiate this, then I get, via the power rule, 4x cubed, okay, which is precisely f of x. Okay, so my antiderivative here worked. Now, in general, yeah, so this antiderivative, you'll see in later videos that this is one specific antiderivative. There is a more general version of it. We'll get to that in a later video though. Okay, so now just as we had a table of derivatives, we can generate a table of antiderivatives. So again, I'm going to have two columns here, f of x and capital F of x. So again, f of x is the function, and capital F would be the antiderivative of that. So I need to think, for little f, what did I have to differentiate to get this? So in other words, the right-hand column, if I differentiate this, I should get the left-hand column. Okay, so the antiderivative of 1 with respect to x, everything we're doing in this table is with respect to x. So if I got 1 out, that means that, well, this would be 1 times x to the 0, right? So via the power rule, I would bring the exponent up into, or the coefficient up into the exponent, and then that would be my function. So I think this is just x to the 1, or just x. Similarly for k, this is k times x to the 0. Now here there's no coefficient, k is the coefficient, but I can always multiply by 1 without changing the value. So again, if I bring the 1 up into the exponent, it would be k, oops, that's a k, times x to the first, or this is just kx. Okay, so in other words, what these two are telling us is that if I have a function that is just equal to a constant, the antiderivative of that is c times x. Okay, so all I've added is, so again, I'm going up, I'm undoing differentiation. If I differentiate cx, then I would get c, just that constant. If I anti-differentiate, I'm increasing by a power of x, at least in the case of polynomials. Okay. Now, continuing through this list, ax, okay, so this is power rule again. A is going to stay there. Okay, A is a constant, I can't change it. But via the power rule, I would have to normally increase the power by 1 to undo differentiation. Differentiation, we decrease the power by 1. And also, I'm going to have to divide by the power. Okay, and that's simply because if I have, so if I take the derivative of x squared, say, this is 2x, okay, because I brought the exponent down as a coefficient and then decreased the power of the exponent. Okay, but now if I begin with x squared, or if I begin with x, I'm missing this 2, so I'd have to move that over to the other side. Okay, and so if you can check it by differentiating again. So this is, if I were to rewrite this, this is a over 2, just collecting the constants, times x squared. If I differentiate this, would have to bring the exponent down as a coefficient, so the 2 and the 1/2 would cancel and be left with ax. Okay, that one might take a little bit of time. You can perform the same thing with other exponents, which we'll get to in just a second. Now, in the case where we have 1 over x, we actually saw that if this was the derivative, then the antiderivative was natural log of the absolute value of x. Now here it is actually really important that you do keep the absolute value signs, simply because we may run into domain issues if we do not have them. Okay, so perhaps, x could be a negative number. We don't want to have the natural log of a negative number. That doesn't exist. Okay, so again, you can check this by differentiating. Derivative of natural log of x is 1 over the input times the derivative of the input, which is just 1 here. Okay. For the next one, this is a power function. So in general, when I anti-differentiate, I'm going to increase the power by 1 and divide or multiply by 1 over, and divide by the exponent, or multiply by 1 over the exponent. Okay, and that's just because if I want to get back to a scenario where I have a coefficient that is 1, I would need to, when I differentiate, the exponent would come down as a coefficient, which would then get rid of this first term, or get rid of the coefficient here. Okay. Moving on, e to the x, the antiderivative of this is just e to the x, same thing. So when we differentiate, we get e to the x times the derivative of the exponent. Okay, great. Now in the case where we have a chain, where we have to have so if we differentiated this, normally we would have e to the bx times b. Okay, but now, again, I'm undoing differentiation, so my e to the bx is still going to be there when I anti-differentiate, but the antiderivative is going to have a 1 over b. Again, because when I do the chain rule, I would multiply, so I need to undo that multiplication. I need to do division. Okay. B to the x, this was b to the x, and then normally we would have times a natural log of b, okay? But again, since we're undoing differentiation, I'm not going to have multiplication, I'm going to have division. Okay, and so right now I'm writing it as 1 over, same thing, 1 over the natural log of the base. You can do b to the x over ln b, same thing. Okay, trig functions are a little bit interesting. So derivative of cosine, so if cosine was the derivative, that means to get that I had to have the original function be sine of x. So again, if you differentiate sine, you get cosine. Okay, and then similarly with cosine bx, I would have sine of bx, but then normally if I differentiate it, I would have a coefficient of b. That is 1 over b. Okay, so just again to undo the chain rule. Sine x, cosine x would be the antiderivative, but there should be a negative in front because remember cosine, the derivative of cosine is negative sine, and here there's no negative present, so there should be a negative here. And then for this last one, it'll be 1 over b negative cosine of x. Okay, and again, you can check, if you want to check that these hold, differentiate everything in the right column, and you should get get the function that corresponds to it in the left-hand column. Okay, take some time, do some examples with these just to make sure that we have these down.